In this video, I want to introduce the subject of rectification and the concept of a superdiode. First of all, a quick reminder about diodes. Diodes are not linear components, in the sense that the voltage across a diode is not linearly related to the current flowing through a diode. For a forward-biased diode, if you double the voltage across it, you vastly more than double the current flowing through it. For a reversed-biased diode, on the other hand, if you double the voltage across it, the current through it hardly changes at all. It's just held at the saturation current for that diode. One common use of diodes is to rectify signals. And rectification means producing an output related to the modulus of the input signal. There are two basic forms of rectifier circuit, the half-wave rectifier and the full-wave rectifier. The half-wave rectifier is only sensitive to one polarity of input signal. In the diagram here, this is the half-wave rectified signal here. It follows the input up, but when the input goes negative, the output of the half-wave rectifier just carries on at zero. So it allows positive voltages to go through, does not allow any negative voltage to go through at all. The full-wave rectifier, on the other hand, does produce a true output, which is the modulus of the input signal. So for positive input signals, it just reflects the input signal. For negative input signals, it outputs -1 times the input signal. So it's always the modulus of the input. You can build both circuits using diodes and op-amps, but in this first talk I'll just concentrate on the simpler half-wave rectifier. The circuits are commonly used to produce a voltage which is related to the amplitude of the input signal. You can't just take the average value of a sine wave and assume that that is related to the size of the input signal, because the average value of a sine wave is always zero. But if you rectify the sine wave, and then take the average value of the rectified version of the sine wave, you do get an indication of how big that incoming sine wave was. Now, this is the simplest possible half-wave rectifier circuit. It's just a diode and a resistor. And it works okay for big input signals, but for small input signals, it's got a problem. And the problem is the forward voltage drop across this diode. You may remember that for any reasonable amount of current flowing through a diode, there tends to be a forward voltage drop of around 600 millivolts or so for a typical silicon PN junction diode. There are other types of diodes which will reduce that forward voltage drop, but they will always have a small forward voltage drop associated with them. And that causes a problem with the output of this rectifier. You see, the real diode is always outputting slightly less than you would ideally want it to be. X is always slightly less than A. We can see this in the simulator as well. Here I've built up the circuit, and you can see that with an input voltage of 0, the output voltage is 0, and that is what we would expect. For input voltages which are less than 0, then an ideal diode, an ideal half-wave rectifier, would output 0. This one, of course, doesn't quite output 0 because there is a small reverse current, the saturation current, flowing through that diode of, in this case, 2 nanoamps. 2 nanoamps flowing through a 1K resistor produces an output voltage of 2 microvolts, so that would be -2 microvolts in this case, since the current is flowing this way. That's not usually a big problem. What is a bigger problem is what happens with small positive voltages. See, 284 millivolts coming in, and the output of my rectifier is only 61.78 microvolts. And as the output and input increase in voltage, that forward voltage drop of around about 0.7 volts in this case starts to become a significant problem. We would ideally like an output versus input characteristic to start at the origin and head up at 45 degrees from the origin. This one isn't. It's lagging behind what we would like. and that's because of the forward voltage drop across the diode. But we can fix that problem with an op-amp. Consider this circuit here, known as an active rectifier, or sometimes as a superdiode, because it works pretty much like an ideal perfect diode would work. Supposing A was a positive voltage, let's say about, 3 volts, going into the op-amp like this. Now, the op-amp is trying in its linear region to keep its two inputs at the same voltage. In fact, if the non-inverting input is at a higher voltage than the inverting input, then the op-amp will be producing a very large output voltage, which will tend to increase the voltage around this part of the circuit until you get into equilibrium, and equilibrium happens when the two inputs to the op-amp are at approximately the same voltage. So this point here would be 3 volts as well. In order to get this point here at 3 volts, the op-amp will have to produce an output somewhere around 3.7 volts, 1 voltage drop higher than the output of the actual circuit at X. But that's exactly what we want. We now have an output of our circuit which is equal to the input. It doesn't have the diode drop between the input and the output because the op-amp is compensating for it. The op-amp is increasing the voltage by exactly the amount that would be required to compensate for the voltage drop across the diode, because the op-amp is trying to get both of its inputs to the same voltage. However, supposing the input was negative, supposing the input was, say, down at -3 volts, then the op-amp is trying to get its inverting input down to -3 volts as well, but it can't. And it can't because this diode is not allowing any current to flow into the op-amp's output. We have a resistor here, which has one end tied to ground, but no current can flow up through this resistor because there's nowhere for it to go. It can't flow this way through the diode into the op-amp, and it can't flow round here into the input of the op-amp because an ideal op-amp has no current flowing into its inputs. So with no current flowing through this 1K resistor, there's no voltage drop across this 1K resistor, the output here is at 0 volts. Not exactly 0 because there is the small saturation current flowing through the diode, but to a very good approximation it is 0 volt output when the input is negative. The op-amp at the moment therefore has 0 volts on its inverting input, -3 volts on its non-inverting input. Its non-inverting input is below its inverting input by quite a long way, and that throws this op-amp into negative saturation, so its output here is going to be lowest possible. It's going to be saturating negative. So we have an op-amp which is saturating negative when the input is negative, and which is one diode drop above the input when the input is positive, which is pretty close to an ideal half-wave rectifying circuit. We can see it working in the simulator. Here I've built up a simple passive regulator here, and our new active superdiode regulator down here. And you'll see that the output of the super regulator is exactly equal to the input voltage, but of our simple rectifier is significantly below the input voltage here. For negative voltages, they both behave exactly the same. For positive voltages, our new super active regulator doesn't suffer from the forward voltage drop across a diode. There are actually several different types of circuits that you can make that are active half-wave rectifiers, and just to finish off this talk, I'll briefly mention another one. This one. This is an active half-wave rectifier that is sensitive to the negative going input signal, and not the positive going input signal like we've seen before. Consider what happens when the input A is negative, maybe -2 volts. The op-amp acts to keep its two inputs at the same voltage, so this inverting input would be held at about 0 ground potential by the action of this op-amp, if it can. And in this circuit it can do that. So we've got about 0 volts here. That means there's a current flowing this way through this resistor. That current cannot flow through this diode because it's going the wrong way, so it has to flow through this resistor here. Effectively, that resistor is taking no part in the circuit whatsoever. That current then will come out of the op-amp's output through this diode here, round through this resistor and back to the input there. Effectively, it's working pretty much like an inverting amplifier. And if these two resistors are equal, then our inverting amplifier would have a gain of -1. 2 volt input would result in a 2 volt magnitude output. The actual output of the op-amp here would be about 2.7 volts, one forward voltage drop across a diode greater than the output voltage, 2 volts. So, if the input is negative, the output will be -1 times the input. However, if the input is positive, say this was +2 volts, then we've now got a current that's trying to flow this way through this resistor, because the op-amp is again maintaining its inverting input at ground. This time, this current can flow through this diode and round to the input of the op-amp there, which means that there's no current flowing through this resistor and no current flowing through this resistor. The output of the op-amp here would be around -0.7 volts at this point. That's one voltage drop across the diode. That's all that is required to get this current coming through the input resistor to flow round through this diode. That means that this diode is reverse biased. -0.7 volts on this side, ground on this side. So there's no current flowing through that diode. So, this point here would be at 0 volts, that point there would be at 0 volts, no current flowing through this resistor, no current flowing through this resistor, the output would be at 0 volts. So for positive voltages, the output is just 0. We'd have a situation here where if the input was doing this, the output would be doing this. -1 times the input when the input is negative, and 0 when the input is positive. But the advantage of this circuit is the op-amp never goes into saturation. It's in its linear region all the time. And often that can help the op-amp react faster. Once an op-amp gets into saturation, it can take a bit of time to recover and get out of saturation again. And that is one issue with the simple superdiode circuit that we looked at earlier. This circuit does not suffer from that problem. Next time, we'll have a look at full wave rectifiers.